My name's Alan Holub. I am, usually when I talk at conferences, I do it on one of two subjects that are related. Is I either talk about agile process, or I talk about architectural topics that are related to agility. And microservices are right in the middle of that space. Is the microservice architectures are almost ideal when you're developing in an agile environment. Because the small size of the microservice works really well with a small team that's doing the agile development. So the two are related, is that I talk on both subjects, as I said. I should say about this particular subject, I'm going to be doing a full 3-day tutorial on microservices in London in November. So if anybody wants to take this a little bit further, in an hour I can only talk about the basics. I can't talk about any of the in-depth stuff. As we'll be looking, in that November class, I'll be talking about some of the same subjects I'll be talking about today, but in much greater depth. So if you want to follow it along further, do that. And the slides are on my website. Is the URL is somewhere. Well, what happened to the URL? It's holub.com/slides. I'll have that URL up in the last slide also. But let's talk about swarming and what that's all about. First of all, swarming systems are systems where you have objects cooperating with one another without any controlling agent at the top telling everybody what to do. And in the case of a flock of geese, each bird is just following the bird that's right in front of it. And interestingly, in the swarms, in the murmuration of starlings we were looking at on the initial slide, the same rules apply, as every bird is just looking at the bird in front of it. However, the behavior of the system as a whole is much more interesting than that. It's much more interesting than you would guess by simply looking at what any one bird is doing at any given moment. Now, the systems are not chaotic. Is the bird in front, for example, this guy, will be in front for a while. He'll get tired, he'll fall to the back of the V, and one of the other birds will come forward. So there's a coordination going on with inside the flock as the flock is moving. But at any given moment, everybody is just looking at the birds that are right in front of it. Now, one of the best examples of that in the mathematical world is Conway's Game of Life, which I'm sure some of you at least have seen. What we're looking at here is this is called a glider gun. And the objects that are appearing out of the bottom here, those are the gliders. Now, the interesting thing about this is that this game is following the same sorts of rules that the flock follows when it's moving, is that every cell is determining whether it's alive or dead by looking at the state of the surrounding cells. If there are too many cells that are alive around you, you die from overcrowding. If there are too few, you die from loneliness. If there are just the right amount, you'll pop into existence or continue to exist. And those are the only rules that are involved. So this behavior here we're seeing, this interesting organized behavior, is not actually programmed into this system. Is that it behaves in a useful way without us having to program that specific behavior. Now, this is particularly important in microservices because when we're talking about lots and lots of microservices all operating at the same time, and when we can't predict how many of them there will be at any given moment, having an overreaching coordinating entity telling the services what to do is just too hard a problem to be solvable. And a lot of the big coordination systems, if you will, have so much in the way of coordination code and so forth in them that it's unconvincing to me that they're going to work. Is that we have to have systems that are more flexible than that. So a system that's adaptive is always going to be better in my mind than a system where you've got some controlling agent that's in charge of everything. And the Game of Life is a good example of that. It's an adaptive system, but the main behavior here is not programmed. So microservices then are a way of applying that kind of thinking to a programming environment, to a server environment. Now, I could spend several hours talking about the characteristics of microservices, but let's talk about a few of the most important ones in this context. First of all, a microservice has to be a completely standalone thing. You have to be able to deploy a microservice independently of any other microservice. So that's the first problem with the big systems, is they need to know too much about the microservices themselves in order to get them up and running. So a microservice should be implementable as a standalone process that you ought to be able to just launch without having to have any kind of complicated system around the outside of it in order to get it launched and hooked into the system properly. And that's the only way that you get the independence that you need for a microservice to be useful. Whole point of a service, in other words, is that you can work on it independently, as you can not just work on the code, but deploy it independently, bring it down independently, deploy new versions. You ought to be able to test things into the system manually by injecting services into the system manually and seeing if they work or not. You can't do any of that if the microservices depend on other things. And in fact, anytime you have a situation where in order to deploy a service, you've got to do something else, as far as I'm concerned, that's not a microservice anymore. What that is a monolith with plugins. And a monolith with plugins is not a microservice by definition, it's a monolith. The second characteristic that's important is that microservices are small. The usual rule of thumb that people have been using for the last year or so at least is they say a service should be the size of your head. And the way that I interpret that is that you should be able to have everything about how the service works in your head at once. The best way to think about this is that you should be thinking in terms of object size. It's that I think a good size, service should be implementable as a single class. And it should be a class that follows all the usual rules about classes and how big things should be. So you get smaller than that, and you have what I guess they're calling nano services now, and there's Amazon Lambdas and that kind of thing. But at that level, you have too fine a granularity, is that the things that are related to each other are not lumped together physically, which makes them harder to maintain. In other words, the controlling principle here, excuse me, is the so-called single responsibility principle. Right? This knife violates the single responsibility principle. It's doing it's doing way more than it should. And more to the point, all of the things that it does are not really related to the other things that it does. So this is a clear violation of single responsibility. But single responsibility doesn't mean you only do one thing. So this corkscrew, for example, is also satisfied or does satisfy the requirements of single responsibility, even though there are 4 things that it's doing. The thing is that all 4 of those functions are focused on a single goal, which is to open a bottle of wine. So the idea is not that you want an object to do one thing, but rather you want the object to be coherent in the sense that the group of things that it does are all related to one another in a tight way. So if you call some method on the object, on the class, on the service, that method might need to change some kind of state, one way or another. Whether the service is stateful or not is actually kind of irrelevant here. And a subsequent call might need to know that that change has happened. Well, if you've got 2 separate functions, 2 Amazon Lambdas, if you will, you can't do that, or at least it becomes very, very difficult to do that. So single responsibility really applies. The other principle that's essential here is the notion of simplicity. This is a quote from the Agile Manifesto, but it's not, which is not an accident. Simplicity is central to Agile thinking also. But services should be as simple as possible. And that's another problem that I have with the way a lot of microservices are being implemented on the big vendor frameworks right now, is that you have to write the service in such a way that it supports the framework. And that not only violates the isolation issue, right, the standalone issue of the services, but it also means that they can't be simple. There's complexity there that shouldn't be there. Anytime I hear the word, it's simple, I get scared, right? Anytime somebody says, oh, this is easy, right? I think that's one of the 2 phrases, in other words, in English that scare me more than anything else is, oh, it's easy, and this is awesome. And when you hear both of those things together, you know it's neither. And so we want to keep things as simple as possible. So my rule with all kinds of programming, and this includes microservices, is the so-called fool me once rule, is that the first time you implement something, you implement it in the absolute simplest way you possibly can. And by simple, I mean really simple. So I never even do things like add extra arguments to functions on the off chance that that will make the function more flexible. I will implement exactly what's needed and nothing else. Now, there are a lot of advantages to that. The code goes together very quickly, for one thing. It's easy to test. It's easy to debug. And it, more to the point, is more likely to work than not because there is less in it to go wrong. Now, if I find myself refactoring, and I say, if I had done this somewhat more complicated thing, if I had this design pattern in place, for example, and the refactoring would have been easier, then I will add a little bit of complexity in order to support the refactor. So I add complexity as a side effect of refactoring when it's necessary. And that complexity tends to take the role of a design pattern or something along those lines. But we want that characteristic in our microservices also. We want them to be as simple as possible and still get the job done without any kind of extra stuff. So if I'm writing code in order to support my service framework, there's something wrong. I don't want to do that. couple other kind of basic issues before we start. You go to talks at conferences like this, and Netflix always comes up. We are not Netflix. Right? Is anybody in this room writing a system right now that has to be the size and have the scalability of Netflix? I don't see anybody raising their hands. Right? Nobody ever does. Right? So we don't have to worry about the things that Netflix worries about. A lot of the solutions that we see, a lot of stuff in Azure, for example, is meant to solve the Netflix problem. But we don't have that. Right? Most of the systems that I work on will run just fine in one 4-core VM in the cloud someplace. I can get reliability by cloning that 3 or 4 times, and then I'm done. I don't have to have any of the fancy stuff that you see supported and pushed by a lot of these microservice frameworks, because our systems just don't need them. So part of the simplicity rule is that we don't want to build the service for a system for a situation that does not exist. If we're lucky enough to have to scale, we want to build a service in such a way that it can scale. But we don't need to build all of the scaling in from day one, because if we do that, it's going to take longer to get to market. It's going to make the system more complicated. It'll be harder to debug, all of the other negatives that are associated with big monolithic systems. So as simple as possible. The other problem that people don't talk about a lot is lock-in, is that a lot of vendors do what they do in order to lock you into their systems. And a lot of what they're saying is essential is not essential, but if you drink the Kool-Aid, right, if you buy their argument, you end up implementing this stuff in such a core way that you are incapable. It's not possible to take your system and move it to some other vendor. And that is always a mistake. All of the vendors have advantages, all of them have disadvantages. You might not want to do them at all. You might want to be running inside your own data center at some point, and you might want to run on the cloud at some other point. You want that flexibility, and you want the ability, even if it's nothing but cost that's driving it, to move from one vendor to another. So as soon as you start leveraging the facilities that a specific vendor is providing, then you are locked. You're locked in. Now, that doesn't occur with all facilities, right? Every vendor has some kind of storage mechanism. And the APIs might be different from vendor to vendor, but of course you can wrap those APIs in a very simple, shallow class that isolates you from the specific API so that you can port more easily. But other facilities are more tightly integrated into the way the system works, and I avoid those like the plague. Almost everything that I'm implementing right now is done on top of a nano VM, which costs about $5 a month depending on who you're getting it from. As Amazon and DigitalOcean both charge $5 a month for their nano VMs. And in fact, Amazon's nano VM, if you were running a computer or a service on one VM, you'd probably be down in the free tier most of the time, is that you're using it so lightly. In other words, that it's not going to cost you anything. So things like Amazon Lambda and stuff, I hate Lambda. I think it's a disaster. But more to the point, it's what they say, which is you're only paying for the time that you're spending. Well, that's only true up to a point. If you spend more than 100 milliseconds inside your function, then they start charging you a lot of money. And you can open your bill from Amazon next month and find an $80,000 bill from Amazon, or a 800,000 kroner bill from Amazon, and they're 80 well, anyway, times 100, whatever that is, or times 10. And the point is that you get surprises when it comes to billing. If you're talking about $5 a month for a nano VM, there are no surprises there. You know exactly what it's going to cost, and it doesn't cost much. And most of us can run our services on nano VMs without any difficulty at all. So you don't want to be locked in. The other issue is the complexity and the hideous difficulty of doing things like configuration. Just look at the service fabric. This is not following the single responsibility principle. Right? The service fabric is a monolith. It's among the worst kinds of monoliths. It's huge. It is hideously difficult to configure. You need an expert just to configure it. Whether it works or not depends on whether you have it configured right. But since it's so hard to configure, you don't know whether it's configured right. If you're going to work on the service fabric, all of a sudden you have to spend a lot of time learning how the service fabric works when that time is better spent programming. It's just adding way too much complexity. So I reject these kinds of systems just out of hand. This is a monolith into which you are plugging things. And microservices are not plugins. They're meant to be standalone, independent units of computation. So as soon as you're plugging your microservice into something, it ceases to be a microservice anymore. It becomes part of the monolith, and you have all of the problems that you have associated with monoliths. So I really don't like this kind of stuff. I also really don't like the notion of orchestration, is that the idea of orchestration is that somebody from outside is telling the services how to work. And again, if that's happening, your services are not independent of each other anymore. They're not independently deployable anymore. My services typically run as standalone processes, and nobody is telling them what to do. So I don't like orchestration either, is what we should be doing. In other words, it's not orchestration, but what's called choreography, where the individual players here, the individual dancers, are paying attention to the dancers around them. They're all following a general theme, but they're not, it's not like an orchestration system where they're behaving to the note in order to do whatever is on the score. So when we implement these things, there's lots of ways that we can implement them. Typically, one implements them with some kind of HTTP front end. Typically, that requires you to have load balancing and things like that on the front of the front end. That in itself is a problem, is HTTP is not zero overhead. Microservices do have to talk to the web, but in most microservice systems, most of the services spend most of their time talking to each other, not talking outside. Most of the microservice systems that we work on will run in a single data center. You're not going to scatter your services over the whole planet. You might replicate your service system in different data centers, but you're not going to scatter the service across data centers. If for no other reason, it's impractical. If you put your data in the EU and you put your functions in the US, there's going to be hundreds of milliseconds of lag every time you need to access your data. It's just not going to work. So generally speaking, everything is concentrated in one place, which means that we don't really need HTTPS. As HTTPS, remember, or HTTP, exists in order to be able to access data across the internet. If we're not accessing data across the internet, we don't need that overhead. The other problem is that it makes our systems harder to implement. Again, the microservices should be very small. And as soon as you start building a web server into your microservice, it's not small anymore. As soon as you start bundling your microservice with Apache or Nginx or IIS or any kind of web server in order to have a web front end, then it's even less small because now the web server is effectively part of your service. And you have a lot of configuration and coordination issues that you would rather not have. So having your services talking with HTTPS or HTTP at the highest level is not actually a very good strategy. Is that it adds inefficiencies, it adds complexity, it takes away independence, and you don't want any of those things to be happening. So what do you use when services talk to each other? And the answer is that you should be using some form of lightweight messaging. Now, messaging is one of those topics that everybody really desperately needs to know about, and nobody knows that. It's always presented as this kind of minor side issue because people are so focused on the HTTP thing that they're not thinking about how do you actually coordinate effectively. There are a lot of messaging systems out there. There's Rabbit, there's Kafka, there's ZeroMQ, which I'll talk about in a moment. And there are bigger systems like Tibco. In a microservice environment, you want the system to be as lightweight as possible. You want the least amount of configuration, the least amount of programming overhead. You want to use messaging, in other words, as a way to talk to other services in an efficient way. So lightweight is a key part of this equation. Now, just to digress for a few minutes, let me talk for a bit about what messaging systems do for you. Messaging systems basically are doing network communication. And they're doing it using one of two metaphors. The first one being a queue. A message queue works like any other queue. It's a first in, first out system. The way that two objects on the network talk to each other is literally by sending a message. The message is a physical packet of data, typically. In my systems, I always use JSON for my payloads because JSON is completely independent of language, is that it's an important characteristic of a microservice that it be both platform and language independent. If I'm writing a microservice system, in other words, if I'm doing string operations, I want to write the service in Python. I don't want to write it in C# or Java. If I'm doing something that's got a lot of logic associated with it, then I want to go to C# or Java or something like that where the logic is going to be easier to implement. I want to use the appropriate tool in the appropriate place, which means that microservice systems are typically both polyglot in the sense that different services are written in different languages and also platform independent. The messaging system allows you to have that independence because two things written in different languages can talk to each other across the network. And if the information is flowing back and forth in some sort of uniform format, and JSON is a good format for that, then you're isolated from the implementation language and even the platform of the other system. So you could have a service running on Windows talking to a service that's running on Linux, and there would be no problem there. The messaging system, in other words, would absorb that. So the basic idea then with our queues, this is the 0MQ situation. So you have a producer and a consumer of the message. On what blue line here is the network. You send a message, obviously, from the producer to the consumer. In the case of 0MQ is a point-to-point protocol, which is one of the things I like about it. So the producer talks directly to the consumer. Now, the problem with that is that if the producer and the consumer are not talking through some central coordinating entity, it becomes difficult to make a connection and then make sure that that connection is reliable. If the connection drops, you need to be able to reestablish the connection, and that should be completely painless. Zero does that for us, which is a good thing. It's one of the reasons for using messaging systems, is all of these kind of reliability issues can be handled by the messaging system itself rather than by you. It's code that you do not have to write. But it's a strict point-to-point thing. Now, in order to make that work, the producer doesn't know when the consumer is going to connect or vice versa. Either one could come up first. So if the producer comes up and starts sending things off to the consumer and the consumer isn't in the system yet, it's got to store messages locally on the producer side, and so that when the consumer finally connects, it can then send them across. So everyone following what I'm saying? Same thing applies on the consumer side. There could be many producers all sending messages to the consumers. Well, you need a queue over here to hold the ones that you haven't gotten around to handling yet. So the queue has to be distributed in a point-to-point system. Now, also connected to this is the notion of connecting and binding. One side has to have an address, an IP address of some sort. The other side has to connect to that IP address. Interestingly, in Zero at least, you can put the bind on either side. So it doesn't matter where it is. The question is, where is it most convenient? Is that in order for this guy to talk to this guy, it has to know its address. In order for this guy to talk to that guy, it doesn't need to know the address. So topologically, you've got to decide how to make that work. I'll talk about that a little bit more in a moment. But the binding can happen anywhere. You can put a broker in the middle of this system. A broker is a separate entity. So if you talk about systems like 0MQ or Kafka or any of the larger messaging systems, they all have brokers. I don't like brokers. A broker is a single point of failure in the system. It is difficult to configure. It couples the endpoints together, which it shouldn't. The only thing you get from having a broker is that the addresses, the bindings, are bound at the broker side. So this guy can talk to that guy. Both of them know about the broker, but neither of them need to know about each other. And that's convenient, but it is not convenient enough to make me think that I want to use these things. Is that brokers, again, are very, very complicated. They're hard to configure. They're very heavyweight. You just don't want to deal with them if you don't want to, or if you don't have to, rather. They're also, again, a single point of failure. If the broker goes down, the entire system comes to a halt. And I don't like that. I want my systems to be more resilient. Microservice systems should be resilient. They shouldn't depend on one piece of the system functioning in order to function. So when you have point-to-point communications, you don't get that dependency. The final thing you get with a broker, while we're on the subject, is you can have multiple queues. The queue is actually in the broker, so you can have multiple queues in one broker. But again, what that means is that if you take all of the queues for your entire system and put it in one single broker, when that broker goes down, the entire system stops. Nobody has any data anymore until the broker comes back up again. And from a resiliency point of view, I don't like that. Now, in terms of sending messages, typically the producer will talk to multiple consumers. With some kind of queue. There could be a broker in the middle, but there doesn't have to be. Typically, when the producer sends messages out, they get sent out in a round-robin sort of fashion, as they just go to the various consumers that are connected. The thing to notice when I'm talking about that is that this is a kind of load balancing. So we talk a lot about load balancing in the microservice world. The question is, do we really need to worry about full-blown load balancing? And the answer is, when it comes to multiple instances of the same service, no. Right? Because if you have multiple instances of the same service, they're all doing about the same amount of work in about the same amount of time. So if you pull that out of the load balancing equation, what you have is round-robin scheduling. And the message system will do round-robin scheduling for us just fine. So by using a messaging system and having the producer round-robining out to the various consumers with subsequent messages, with a series of subsequent messages, we eliminate the need to load balance between multiple instances of the same service. We just don't need to do it anymore. So we can simplify things a lot, again, by just relying on the messaging system. I'll also say as an aside here, you often hear about message buses. A message bus is nothing but a broker if you had a situation where you had one queue in the broker. Right? So you can think of a message bus as just being a fancy way to say queue, is that it's basically the same thing. Now, the other metaphor that people use in messaging systems is the publish-subscribe, the pub-sub metaphor. You have a publisher that publishes events. You have a bunch of subscribers that are interested in hearing about the events. What you publish is a specific topic. In this case, there might be a couple topics. I'm assuming there's a blue topic and there's an orange topic. So you could subscribe to the blue topic, or you could subscribe to the orange topic, or you could subscribe to both of them. When the publisher publishes, they publish on a specific topic, and then that is routed to whoever subscribed to that topic. So there is no round-robining. It's a broadcast kind of situation. Pub-sub's a little bit faster. It's a little bit better in many situations than queuing is, but it's not a replacement for queuing. It's very difficult. Sometimes you just need queues. And one of the downsides of some of the messaging frameworks that I've seen, like Kafka, is they just give you pub-sub. You can fake it in Kafka. You could have a single subscriber subscribing to a single topic, but that's kind of work that I don't want to do. I don't want to worry about it. I'd rather have the messaging system, in other words, handle both metaphors for me. So ideally, you want both publish, subscribe, and some kind of queuing system. And of course, you could add a broker to the middle of this if you wanted to, but there's no requirement that you have brokers there, assuming that you've got a messaging system that can do point-to-point. So by going to messaging, we get a lot. We get a lot of simplicity in our system. We're pushing a lot of stuff off to the messaging subsystem that we would otherwise have to write ourselves, things that are giving us reliability and so forth inside the code. We get a lot of efficiency when compared to HTTP or some sort of heavyweight protocol for talking across the network. It's easy to distribute this stuff. In the case of 0MQ, everything's done with TCP IP addresses. So if they're all on the same machine, your system is running on the same machine. If they're on different machines, they're suddenly running on different machines. So it's easy to do distribution. And we have complete language independence because the messaging system itself is language neutral. We can have a service written in any language talking to a service written in any other language. So looking at 0, it's called 0 because there are a lot of issues. I will apologize in advance for the fact that they've used an O instead of a 0 here, as they don't understand the difference between letters and numbers, I think. But but this is the official logo of 0MQ. It is 0 all of these things. No brokers. It's not 0 latency, but it's close to it. It's very, very fast compared to a lot of the other protocols. There is literally no administration. The only downside of that is there's no administration console. So if you want to monitor the system, the behavior of your system with a pretty picture, you have to write the program that's doing that. That's not part of 0. As other messaging systems will have monitoring consoles that come as part of the system. It doesn't cost anything. It's open source. It's free. It runs on every platform. It's generally a good thing to be working for. I'll skip past this slide quickly because you have access to the slides if you want them. But you can get information at this URL. It was written originally for financial applications, so it's very reliable and also very fast, right? It's good for real time. It runs on pretty much every platform. It runs fine on .NET, it runs fine on Linux, it runs fine on the Mac. It actually runs on several of the IoT platforms as well, some of the IoT operating systems as well. More to the point, there are bindings in every known language, including Ook. I don't know if anybody here is an Ook programmer, but I didn't even know what Ook was until I saw that 0 had a binding for Ook. But if you want to program in Ook, you can do it. But more to the point, it supports the languages that all of us are using, is C# and C and C++ and Java and Python and all of the standard languages. So you can write a program in any language and it can talk to 0MQ. It supports pretty much all of the networking program or protocols you would care to use. I usually use TCP because it is the most common of them. It'll work everywhere. And it has a security wrapper that goes around it that you can use to make your messaging secure. One of the big flaws that I see when I look at microservice systems is that people are not thinking of security inside the data center, and you have to. Right? If you think about the notion of a denial of service attack, in a microservice world, the denial of service attack isn't necessarily outside the data center. If a service goes crazy, it could be sending out hundreds of thousands of messages. And receiving those messages could generate hundreds of thousands of more messages, and you could have a cascade of messages that makes the system completely dysfunctional, and that could be happening entirely inside the data center. And that might happen because of a bug, and that might happen because of something from the outside, but it will happen. So thinking of security as being a boundary thing, something that if you don't let in the bad guy, you're okay. You can't think that way. So one of the things that's nice about Zero is that we can encrypt the actual messages, is that it uses elliptic curve encryption around the actual messages. The final thing I'll say about it before we start going a little bit more into architecture is this is the entire API for ZeroMQ, and half of these functions are functions that I've never used because I haven't needed to. So it's a very, very simple system to learn, is you can learn it in an afternoon, is that it's, and get up and running efficiently in an afternoon. The basic metaphor is the notion of a socket. This is not a Unix, Linux style socket. It's really a port into the messaging system. The basic idea is that you plug into a socket. The socket is an asynchronous front end to a queue of some sort, or it does a pub-sub kind of thing. You can have multiple endpoints, so a socket could have multiple IP addresses bound to it. On the other end, a socket could connect to multiple IP addresses, so you can feed into a single socket from multiple sources, or you could have multiple sources feeding out into as many targets as they want. You could have different IP addresses associated with the same socket if you wanted to. More commonly, you'll have different port numbers associated with the same socket or different protocols associated with the same socket. You can even have multiple transport protocols associated. So you could have TCP and something else for the two protocols. It does all of the threading for you. So your services can be single-threaded, which is a good thing, is that in general you don't want to put multi-threading into services because it's another layer of complexity that you would rather not have. It's another source of difficulty. If you think about queuing, instead of doing 4 things at once, if you queue those 4 things up and do them one at a time, you don't need to coordinate anymore. There's no need for threading anymore. Connection and reconnection we already talked about. So let me look at just one simple example so you can see how this all works. This is a simple request response or request reply system. This is the easiest kind of connection to make in the Zero world. You make a request to a client makes a request to some server in this case. The server replies. This is synchronous in ZeroMQ, is that you can make a request to the server, but you can't make another request until you've gotten the reply back. You don't have to block while you're waiting for the reply, but generally you do. So you make a request, you get a reply. And a client could be requesting things from multiple servers. Here I've got the connect on the server side and the bind on the client side, but it doesn't, again, have to be that way. You could flip things over if you wanted to. So that's 2 objects talking to each other. If we look at the code for this, I'm going to skip through some of it. But the basic idea, and this is the way Zero works pretty much everywhere. And this is Java, but the C# APIs look almost exactly the same. You start up, in this case, I am implementing the client and the server on separate threads, so I'm going to start up the server with just a call that's going to start the server thread running. This is the ZMQ stuff. You create a context. You ask for a socket. In this case, it's a request socket, so you have a request socket talking to a reply socket. You might also have a publish socket talking to a subscriber socket. There's a push socket that you can talk to a pull socket, and so on and so forth. So you decide what the socket type is. And then in this case, on the client side, I'm connecting. And then I send messages off just by saying requester.send. In this case, it's just a string. You couldn't get much easier than this, right? As you establish the connection, you send strings across. In the case of the microservice stuff that I'm doing, these strings are JSON strings. They are, you can think of them as an RPC system, is that I don't use REST, right? If you think about REST, REST is really a data-centric protocol, right? Is the idea in the REST protocol, if it's pure REST, is that the URL specifies the location of some resource, and the verb, right, get, put, post, whatever verb you're using, specifies what you're supposed to do to that resource. When we're talking about microservices, you're not getting and putting stuff. We're thinking objects. So you shouldn't be getting and setting things from objects in any context. What you should be doing is asking the objects to do work for you. So the basic idea here then is that the protocols will be used to request some objects. So we'll look at a little bit of JSON in a moment, but the basic idea here is that what you're sending is a JSON packet that's requesting that the service do something for you. It tells you what you want it to do. You pass arguments in. It responds with the JSON packet that's got the result in it. All right? So this is our basic sending code. The receiving code looks almost the same. You have a context, you get a socket out of it, you bind on this side. Remember, we connected on one side, I'm binding on this side. On this side, I'm receiving the string instead of sending it, and then I'm looking at it. If it starts with stop, I'm going to stop the service gracefully. If it doesn't, I'll do something and then spin back up and get another request. But the point of this is not a 0MQ class. This is, but I just want to show you that this actually is easy. As I said, I usually run in terror when I hear somebody say that, but hopefully you'll make an exception here because I've proven to you that this actually is easy. So, and as I said, there are bindings for pretty much any language you want to program in that work with this. So, moving back into the direction of the swarming systems. The swarming systems that I'm building are all built on top of messaging. The microservices use messages to talk with each other. Now let me explain then kind of the evolution of my thinking as I moved in the direction of the system I'm going to get at. This is where I started with a web server called Mongrel 2. Mongrel 2 it's written in Ruby, so people in the Ruby community know more about it than anybody else does. But the basic idea of Mongrel 2 is that Mongrel 2 is a translator. It takes HTTP in on one side and it generates 0MQ messages on the other side. So the way that you plug a service into this web server is by writing a service that pulls messages off of some queue where the portal here, Mongrel itself, is pushing messages. So that means that the service is not plugged into the web server in any physical ways. The service could be running on a different machine in a different data center. They connect across the messaging system using a TCP IP address. So it's a standalone thing. Mongrel, the way you configure Mongrel is with a simple table that just maps URLs to IP addresses. It says when something comes in at this URL, send a message, take all the post data and stick it inside of a 0MQ message, and then send it off to this IP address, to a queue on this IP address. And then it gets a response back. Gets the response back, interestingly enough, using pub sub. So it pushes and pulls here, and then it publishes and subscribes to get the result back. I'll talk about why in a second. So what this got me thinking about is that HTTP is just another service, or at least HTTP translation is just another service. If you look at your services, in other words, as a cloud of standalone objects that are sitting on a message bus and sending messages back and forth to each other, and they're not using HTTP to communicate to each other, well, we do have to talk to our services from the outside. So that talking can be done with just another service. Something that does nothing but receive HTTP post requests, for example, and turns them into messages and routes them off to the correct server, the correct microservice, if you will. So that's where I started. Now, Mongrel is not good enough as it stands to run a microservice system, but the thinking is good. Huh?
What if Mongrel goes down?
Then you're doomed, right? So that's. However, you can run multiple instances of it. So you could put all of the usual infrastructure in front of this. You could have multiple instances of Mongrel. You could have a load balancer in front of that. You could have a reverse proxy in front of that, and then you're isolated from the Mongrel itself going down. So you can use replication to do that. We can have multiple services on the bus, of course, and remember they're going to round robin. So the portal is just going to, if they're all bound to the same socket here on the portal side, they're just going to round robin through them. So we can scale simply by replicating the service. So that's the first thing in the direction of swarming, is that the first characteristic of a swarming microservice is that it observes when it's too busy and clones often instances of itself to handle the extra load. So a swarming system, the services are self-replicating. A service needs to know how to make a new version of itself. In the framework that I'm using, it does that by just shelling out to a shell script, which does whatever it needs to do in order to get a new instance of itself running. It might be using a Kubernetes cluster to do it. It might just be spawning a process. So the point here is that the service does need to make a copy of itself, though, when load increases. And what will happen then is the way you handle load is that as the service gets too much load on it, it starts making clones of itself. Since the thing that is making the call is round-robining between the clones, then the load is now distributed pretty much evenly between the clones, and your load goes down, your load factor goes down. You could keep the extra ones around indefinitely. I don't like to do that, so I do have a mechanism for getting rid of the clones when they're not working hard enough. I'll talk about that in a second. But that's a less time-critical issue, right? If a clone hangs around for 10 minutes and it doesn't happen to be working, it's not a big deal. It's not going to It's not going to cost you much in any way that the word cost means. Next order of business is that we could have more than one portal, as I was getting at that earlier. That way they could be running in parallel and we can have a little bit of a robustness. We'll put the normal load balancers and so forth in front of the portals in order to get load distributed properly. The reason it's pub sub is that what happens is that when the portal gets a request, it puts the topic name into the request that it pushes to the service. The service then publishes the result to that topic. So all of the requests that came from this portal will have unique topic IDs that match the request to the response. And all of the ones that come from this portal will have unique and different topic IDs. I guess that's what unique means, that they'll be different. But the point is that the service that handles the request just publishes the response and it doesn't care which portal it goes to. Is that it's going to the one that subscribes to that topic, and the one that subscribes will be the one that generated the original request. So pub sub on the response side makes it much easier to reply to a service to send a result back, because you don't have to know who sent it to you. It's kind of a basic rule of object-oriented systems that you shouldn't know who sent you the message. And then finally, we can put things like logging just right on these buses. And if we do that, we don't even have to log. All right. Now, also, we could have multiple portals feeding multiple buses. So every one of these blue lines is effectively a broker in the Mongrel system. And so you'd have one broker per microservice. And then on the other side of those brokers, there would be as many instances of the services that you needed to handle the load, handle the current load. And of course, we could have multiple portals feeding multiple buses if we wanted to do that. This is characteristic of messaging systems, as the diagrams get really messy very quickly. Okay? Now, so I started out with Mongrel, and then I started thinking Mongrel's not good enough really for doing a microservice system. It doesn't handle security particularly well. There's just a bunch of things about it that I didn't like. The fact that I had to implement services using brokers was the worst part, though. But even then, even saying that, I started building a microservice platform, which I'm calling Janus. There's going to be a URL, janusframework.org, doesn't quite exist yet, as I'm not quite ready to put it up on GitHub, is that I should be ready in a month or two. If you go to that 3-day thing I'm going to do in London in November, it'll be done by then, and we can analyze. I'm actually planning on spending a lot of class time analyzing the source code for it in that class. But this is version 1. I'm not completely happy with version 1. I'll talk about version 2 in a second, but again, I want to talk about my thinking as we went from point A to point B. Here I had the browser. This is a very Mongrel kind of system, right? Is that here's the HTTP service, which is just a microservice running on this system. There could be multiple instances of it. There's a simple naming service, so we're using 0MQ to talk between these two elements. The naming service is going to do a Mongrel-like thing. It is going to connect IP addresses to URLs, essentially. This naming service was a somewhat more complicated naming service than I wanted in this version 1 system. In particular, when a service instance, when I created a new service, I had two choices. Either I could have a broker, or I could eliminate the broker and have each service talk to the naming service every time it came online, so the naming service could effectively be doing my scheduling. And that was making the naming service way too complicated. It wasn't just naming anymore. It was doing too much. So I reluctantly put a broker in place, but now I've got a broker in place. So the service then is effectively the broker, which is talking to the individual instances. Now, these individual instances were self-scaling in the sense that when they noticed there was too much load, they would spawn off a new instances of themselves and talk to their broker. The broker had a single address. It knew about the addresses of the instances, but the outside world did not. So this is most of the way there, but I still have this single point of failure sitting here, and I really didn't want that to happen. So is everyone understanding what I'm saying here architecturally? So this was a reasonably good approach, but it had its issues. Now, in this system, though, there were a few things a few design considerations that I had that were that applied to version 2 too. So let's talk about those. The first question is, what do you do with a singleton? Right? A singleton is a one-of-a-kind thing, right? And those are our single points of failure. Those are the places that I want to avoid. So in the case of this original system, and I'm just still doing that, I'm handling the singleton problem in the easiest possible way. I'm just spawning off multiple instances of it. Is that most of us get by just fine with 2 DNS servers. Right? That's enough robustness to handle most of our problems. I think if you had 3 or 4 DNS servers, that would be more than you could ever need. Right? I've had no problems with 2. I just run them in parallel. They both work exactly the same way. I'm using pub/sub to talk to them. I ask for an address. I get 2 responses back, and I throw one of them away. And that works just fine. So I'm requesting by pub/sub there because I don't really want to, right? I don't want the naming service to know how many things are talking to it. So by using pub/sub to get the stuff, to get the replies back, that handles that problem. Reliability monitoring is also an issue here. I have to have a monitoring system. The logging system is another singleton. There's a logging service, 2 instances of it that are running in parallel. And the logging system does accumulate logs, but I'm not really doing much with them. I really dislike the idea of having some global level service getting reliability by observing the logs, observing when a service goes down, and then relaunching it. Because we're getting back to another single point of failure in another place where we have complexity. I would rather that the system scaled by itself. So we'll look at the final architecture in a minute, but the way I solve the reliability issue is by handling heartbeating between the sender and the receiver of every message. So if you think about the idea of a heartbeat is that if something is unresponsive or just isn't being used for a while, you ping it to see if it's still alive. And if it's not alive, then you can do something about it. You can launch a new instance. So the basic idea here is that if I'm going to send a message to a given service, if I'm sending messages at a fast enough pace, I know that the receiving service is alive because it's responding. If I don't need to send a message for 10 minutes, maybe 5 minutes into that, I might want to ping it to see if it's alive so that another 5 minutes from then I can send the message and not have to worry about it getting there. So I'm putting the responsibility of detecting when a service goes down on the message senders. Right? Is everyone following what I'm saying here? Rather than on some centralized system that is keeping track of what all of the objects in the system are doing. So that again distributes the reliability out amongst the entire set of microservices so I don't have those single points of failure anymore. The ramping up algorithm is pretty straightforward, is that 0 doesn't give you access to queue, so you can't do it with queue length, so I'm just doing it by load. If I'm so busy that I'm hardly ever doing anything except working, then I'll spawn off a new instance. Now the rest of this stuff, let's just table that for a second. I want to go to the next slide to explain how the rest is working. All right, now, so it's a simple matter though of every service is responsible for cloning off itself when it gets too busy. So, I'm going to sit on this slide for a moment. I'm going to go to talk about how it works, and then I'll come back to it. We have a requesting service, and we have a receiving service. And remember, everything is a service. So the HTTP is being handled by a service that is no different than any other service. The only difference is that it has a port to the a port 80 HTTP connection to the outside. All right. Now, the payload here is going to contain the name of the function, if you will, that I want to call, and the arguments to that function, and some unique request ID. So that's just generated by the sender. Actually, it's generated by the framework. I probably should have shown it here, but there's a framework class here, and there's a framework class there. So in terms of implementing on this thing, you don't have to do any of this overhead. It's done for you by the system. But the basic idea is that it will push this request down to the service. The service will then do whatever it has to do, and then it will respond. And it responds, again, ignore this for a second, it will respond with the original request ID so that this guy can match the request to the response, and then there's some JSON that describes what the response is, and that's going to be unique to the request. So the basic idea is that I'm pushing and pulling here, and then I'm using pub/sub to go back in this direction. Now for this to work, the binding has to happen on this side. The requesting service has to know the address of the service that it's talking to for this to work. So is everyone following me here? All right, so this guy's going to connect, this guy's going to bind. And also, the subscriber connects to a bound socket on the service that publishes the response. So the requester knows the address of the requested service. So the hard part here is discovery. The hard part is how do you learn what the addresses of the services are? So let me go to the next slide, and as I said, I'll come back to this one. I have my HTTP gateway service here. I have a couple of logging services running in parallel. I've got a couple of naming services, and then I have the service I want to talk to. Now, this naming service is a very, very simple naming service. The role of this naming service is to get the first one. It has one service name in it that's matched with one TCP IP address. So the way this all starts, the way the whole system starts, is on the very first call to the system, the sending service goes up to the naming service and says, get me the address of the yellow service that I want to talk to. Right? So it's now got that address over on this side. Since it's got that, it can now send a message off to it. So now the sending service and the receiving service are happily talking to each other. There's nothing earth-shattering here. Now what gets interesting is how does the system scale? The sending service in that JSON packet, I'll come back to it in a second, had a table that had all of the addresses for all of the instances of the receiving services in it. Initially, that table will have just one address in it. So effectively, the sending service is sending the address of this service to itself, to that service in the first time. What it gets interesting is that this service then gets so busy that it needs to scale, so it clones off an instances of itself. The cloning service knows the address of the cloned one. So it modifies its internal table to now have two addresses in it, both the red address and the yellow address. And then when this guy replies to the request, it sends the new address back over to the requester as part of that response. So now the requester has both addresses, it adds the new service to its socket, and now it's round-robining between them. So everyone's seeing how this is working. I can't see most of you, so if you're nodding, I probably can't see you. But so, and the same thing keeps happening, right? If it spawns off, if it has to spawn off a clone, the thing that did the spawning knows where it is, and then when it replies to that message, it sends the reply back up to the original requester, and away you go. So if there are multiple requesters, this table, I should have shown it on both sides, exists on both sides, right? Everybody knows everybody's address. So if another requester comes in, it'll get the first one from the naming service, but in the reply, it gets a list of every instance of the service that exists right now. So I'm essentially doing discovery inside the request and the reply services by passing this table around. And again, this is not code that I have to write. I'm writing a microservice framework just to do this, right? It's doing all this overhead for us. But what this means is we can eliminate the need for discovery. The discovery is happening dynamically just as a side effect. It's an eventual consistency system because you don't know the addresses of all the service instances immediately, but they will propagate out to the entire system eventually. All right, this is making sense to everyone. So if we go back to the authentication, I forgot to mention that. I'm doing authentication here in the framework class that's on the client side. It's on the service side. So the throttling is also happening here. It's not real. I've been going back and forth about the throttling. You really want the throttling to happen here, but that's hard. So I'm doing the throttling on this side. And the way the throttling works is that it just immediately rejects the request. So it doesn't take much time, but it takes some time to throttle. All right, so getting back to here. So here is that table, right? This is the list of instances. So the list of instances goes across as part of the push. If it clones off something, it just adds the IP address, and then it goes back. And I'm using the very simplistic rule that if the push-pull pair is at a given address, the pub-sub pair will be at that address plus one added to the port number. So I assume they're on the same machine, obviously, but they'll be at different port numbers, right? But they're consecutive. Right? So the addresses are always even. As the odd port number is the pub-sub pair. All right? Mm-hmm.
How does the service communicate to the other service that it created a new instance so that the table of all the IP addresses is replicated through all the services?
The question is, how does the service basically transmit the information about the service? How does the replication happen? The short answer is that every service instance has a copy of the complete table. And every service requester has a copy of has maybe a complete copy, maybe not. But the point is that table goes from the client to the server every time a request is made. So if there's any communication happening at all, eventually your tables are going to get updated. Right?
But when you spawn up a new instance of that service,
Mm-hmm.
do other services that don't know the new address?
When you spawn off a new instances, the existing requesting services will not know the new address. That's correct. But the next time they make a request, they'll get that address because the service that they're making the request to does know the new address.
Okay, but if I go into the round-robin fashion, then I contact the first service?
It's eventual consistency. It might take 2 or 3 calls before you get it, but you will get it eventually. Right, and eventually, the worst case is that you have to hit all of them. I haven't seen a situation yet where I've had more than about 7 or 8 instances of a service running, so it's not going to take that long. It's not like you've got thousands of them. We're not all Netflix. All right, is everyone seeing how this is working? So that's the basic system. So I'm basically taking the discovery issue and I'm putting it into the request and reply services so that they can scale automatically. And by doing that, I eliminate the need for any kind of coordination, orchestration framework, right? Is that the services just launch. The thing that starts it up is this simple naming service, which is just simple key value pairs, right? Is given its a logical name and a physical name for the first one. The other thing I'm doing is that I've built into the code for the system a little bit of load balancing in the sense that the service instance that is on the in the naming service will be used less often than other service instances if there's more than one of them. Because everybody's going to hit the first one. Everybody's going to hit the naming service and then hit the first one the first time they make the call. So I want to keep the load on that one a little bit lower. And I'm just doing that with a constant value right now. I just don't call it half the time. All right. The only other issue here is shutting down. We could just wind down easily or wind down quickly. If a service just shut itself down abruptly, the only downside of that is the tables will now be invalid, but that's an easy problem because you make a request and you get an error back from the messaging system and you just remove that one from the table. The downside is that if the services just shut themselves down abruptly, you can have a situation where no instances of the servers are running. They all decide to shut themselves down, and I didn't want that. I wanted one of them to continue to exist. So I hit on this algorithm to do it. I'm still fiddling around with this algorithm. But the basic idea is that when a service wants to shut down, it locks itself so that all subsequent requests are rejected. And then the service that is shutting down, remember it's got that pub subsocket, it publishes a request out to all of its siblings saying, I'm about to shut down. If any of them reply with I'm locked, right? In other words, if they can't send it out, then it says, okay, there's another one shutting down. So in that case, what it does is it gives up on shutting down, backs out of that process by some random amount of time, and then tries again. So this is, if you've ever programmed in Corba, this is the way Corba worked. I'm beginning to think that this is probably more complicated than it needs to be. I could just say, if you are the first one to be launched, don't shut down, and if you're anything else, just shut yourself down abruptly and don't worry about it. I'm leaning in that direction right now. All right. So that's the system I've been working on, is that the basic idea then is that the services are completely independent. They are not sitting inside of some elaborate framework. They are sitting in a framework in a sense that they're all sitting on the same message bus. There's a certain amount of work that has to go on to get all of the communication that we were talking about working, but that's a relatively small amount of work, and that will be the code that comprises the system that I'm working on. If you're interested in following up on that, by all means, feel free to send me an email address or a DM on Twitter. I'm doing that session in London in November, so you can get more information in that in the London conference if you want to go there. And I'm, of course, happy to answer your questions. We don't have any time for that now, but I will hang out here and hang out outside, and I'm happy to answer your questions. So thank you very much for coming to my session.